Good morning, distinguished guests, ladies and gentlemen. Welcome to join us at the Laureate Lecture of the 2016 Tang Prize in Sustainable Development. To begin with, let's start by watching a video message from our laureate this year, Dr. Arthur Rosenfeld, to share with us his joy in receiving this year's Tang Prize. Let's play the video.
Good evening, ladies and gentlemen. I'm Art Rosenfeld. I'm an emeritus professor of physics at University of California, Berkeley, on the main campus. And I'm also emeritus distinguished scientist at Lawrence Berkeley Lab, which is the national lab on the hills above the campus. I'm really sorry. I'm devastated. Je suis désolé that I can't be present in person to participate in the glorious program. But my doctors won't even consider the idea that I tried to get to Taipei and back, hopefully back. So my former graduate student and my good friend Ashok Gadgil, who is now professor of civil and sanitary engineering, has agreed to go to Taipei for me, introduce me for the prize, and appear in the lectures which follow this brief introduction. Ashok has gone from my valued, we've changed the relationship gradually over the years because of Ashok's interest in serving the underserved in the developing world. And the relationship has gone from me being the mentor and he being the mentee, slowly over the years, to work as colleagues. We published papers together. And now he's the mentor and I'm the mentee. And thank you, Ashok. And thank you again, audience, for this great tribute. Thank you.
And now, please welcome to the stage the host of this lecture session, Dr. Yuanze Li, former president of Academia Sinica and Nobel laureate in chemistry, to give us the introduction. Ladies and gentlemen, please welcome Dr. Li.
Ladies and gentlemen, it is my great honor to chair this session this morning. As you know, the Tang Prize for Sustainable Development this year is awarded to Professor Rosenfeld for his innovative research in energy efficiency, which led to a tremendous saving in energy consumption and the reduction of emissions. So he really made tremendous introduction. He was a physicist. He was the last student of Enrico Fermi in the University of Chicago. But in the 70s, when he saw the energy crisis, he decided to dedicate his life on the issue related to energy. He invented like high-frequency ballast to make the compact fluorescence lamp possible, and he made a smart window. But most importantly, he did influence policy issues to convince the government, Jerry Brown, to set the standard for refrigerator, air conditioner, so the refrigerator we are using today only consume 1/4 of the energy of the refrigerator we used in late 70s and 80s. And if you look at California, the energy consumption is flat and only consume about 60% of the US average. And this is called Rosenfeld effect. And now we have an energy unit, 1 billion kilowatt hours of energy is called 1 Rosenfeld. He's really a tremendous scientist and made tremendous introduction. As he said, he could not come today, but the first student he took, Ashok Gadgil, is here. We are so happy that he's here. He's a senior scientist in the Lawrence Berkeley Laboratory and also professor of civil and environmental engineering in the University of California at Berkeley campus. He's also an expert on energy efficiency, but he also worked on the computer engineering on the airflow and pollution flow in the indoors. And he also worked on the water purification. It was very important to know that he tackled the problem of arsenic in India. Bangladesh is now engaged in a 100 million big project to purify water. And the other day, when he was talking, and he said the most reliable data of arsenic really came from Taiwan. And in Taiwan, we have something called Wu Jiaobin. A long time ago, a scientist worked on this, especially a Vice President Chen Jianren, he worked on that issue. And so we have lots of common things that we are doing and what Ashok is interested. And today, Ashok is going to give a lecture on behalf of Art Rosenfeld. As Art was saying, Ashok was his student, his co-workers now become a mentor and working together. Well, let us welcome Ashok Gadgil to the podium.
Thank you, Professor Lee, for a very kind, generous introduction. I had the good fortune to work with Art Rosenfeld from a very early time. Right in 1975, when Art Rosenfeld changed his career trajectory from particle physics, experimental particle physics was his field, and he was a distinguished scientist in that area already. He changed his field to energy efficiency in 1975, the same time when I had finished my coursework and wanted to be looking for a thesis advisor. So I'm going to quickly outline Art's trajectory of his own research life. Very briefly, the period before he started working on energy efficiency, and then pay a lot more attention to his work after 1975, which focuses on his work for which he has received this amazing distinction of being selected for the prize, the Tang Prize in Sustainable Development. So in his life, Art has inspired thousands of people, I'm one of them, to take up this important topic and advance the state of the art and actually state of practice in how we deal with energy in social applications. He's known for his quick wit. You saw in the video, even now he's joking about coming to Taiwan and hopefully coming back. He's a fun guy to work with. His unrivaled personal energy and his generosity makes him a beloved figure in the field of energy efficiency for all those who have come to work with him. And he has an amazingly important knack of looking at a complicated, multidisciplinary, multidimensional problem and figuring out what is the right question to ask. To me, that is the most difficult part of doing research. We all learn how to answer a question when we take courses. We always are able to answer questions in exams, and maybe we get an A and an A+. But the questions are set by the professor. In the real world, there is nobody here. There's just a problem. And we have to say, what is the question to ask? Whose answer will solve the problem? So it has an amazing insight, that ability. That is what takes tutoring or mentoring. And that is why we do PhD under a mentor. So Art has that extraordinary ability. And he conveyed that onwards to people who work with him. Quick background, he was born in the state of Alabama in 1926. He spent the very early years of his childhood in Egypt. His father was an advisor to the government of Egypt in agricultural irrigation. So his family was in Egypt at that time, in his early childhood. Maybe because of that, from very young age, he has a big international perspective. Always he was friends and encouraging to foreign students whom he came in contact with at Berkeley. He finished college. He finished his bachelor's in college in physics at age of 18 and joined after the war University of Chicago, where he was Enrico Fermi's last PhD student. From there on, he came to UC Berkeley and Lawrence Berkeley Lab and led a distinguished career working in the group led by Luis Alvarez, who is also a Nobel Prize winner in particle physics. But everything changed with the oil embargo of 1973. At that time, the embargo was so serious that people in America were beginning to wonder if American prosperity was at risk. What looked like an inevitable, powerful economic growth of prosperity for all of America had suddenly come under a cloud. And Art started asking questions. He said, let me take 2 years away from doing particle physics, only 2 years leave from particle physics, and try to see what I can do about energy efficiency. Of course, he never went back to particle physics because he opened the doors on a very important, very big field. He started asking questions like, why in the Bay Area, in the San Francisco Bay Area, lights were on in all skyscrapers all the time, day and night. We never turned the lights off. It turned out that the buildings were hardwired for the lights to burn all the time. There were no light switches. The light switches were only with the circuit breakers. Same thing was true when we were working at Lawrence Berkeley Lab. There were no switches. The lights were on all the time, and Art would be the last person going home, usually. I would walk out with him, and we would go to the circuit breakers and turn off the lights one by one, banks of overhead lights. And then the next morning, the janitors would turn them on. So this is the level at which we were using up energy in the United States at that time. But there is worse. California homes in 1975 were using the same amount of energy for heating in mild California winter that individual average homes in Minnesota were using for heating in Minnesota winters. And you would say, what's going on? Nobody was bothering to look at it. What was going on was California homes, because of mild, very mild weather, remained uninsulated. They had no insulation was required. So you turn on the heat and you lose heat through the windows, you lose heat through the doors, through the ceiling, through the walls. Minnesota homes, of course, were well insulated. But the interesting thing is they were spending, therefore, the same amount of energy for heating in Minnesota as they were spending in the Minnesota winter, as they were spending in the Bay Area winter. Bay Area winter is very, very mild. So we're saying, what can you do about this? And we'll come to that in a moment. Electric utilities in 1975 in California, when I was a student there, were giving away incandescent lamps for free, 150 watts and 200 watts of lamps. Each lamp was 200 watts because the thinking was, if you give away high-intensity light bulbs in exchange for 50-watt light bulbs, then people will get used to high light in their homes. They would like it. Electricity consumption will go up. We'll build more power plants, and the utilities will make more money, and the stock owners in the utilities will make more money. So it made good business sense to give away 200-watt and 150-watt incandescent bulbs to residential customers if they brought in a dead 50-watt light bulb. You get a 200-watt light bulb free. So you go home and plug it in, and now everybody's happy, you think. That is what was going on. I'm giving you examples of rational behavior of society, and art spotting it and asking questions, saying, what is going on here? People in Eichler homes, which are very popular standard model home that were used in California, were using electric resistance heating for keeping the houses warm. For those of you who know a little bit of engineering, you know that electricity is the lowest entropy form of energy you can get, 100% convertible to mechanical power. You are heating your house to maybe something like 24 degrees Celsius. You certainly don't need to use something as fancy as electricity. All you need is, if you needed to have it, you could use a heat pump, or much easier use gas, natural gas. But that was what was going on. But in Eichler homes, there was no insulation either, again, following the standard California example of other houses. So the big question is, what activities and what needs of society was causing the US to use that much energy? And what were the laws of physics that set the limits on how well you could do in meeting those needs? And what were the societal drivers that caused American society to behave that way? So that was the big deal. That was the reframing of the question. So the reframing of the energy problem is why Art Rosenfeld, Art short for Arthur, that's how he's known, that is why he gets the respect and the love to be called the godfather of energy efficiency. Before the time of Arthur Rosenfeld, the standard question everybody asked was, how do we supply enough energy to meet society's goals? Everybody worried about how much more energy we need, how much oil we need to import, how many nuclear power plants we need to build, and so on. Art reframed the entire question by asking a bigger question, stepping back and saying, how do we accomplish society's goals more efficiently and cheaply? Which is an entirely different discussion then how do we supply enough energy to meet society's goals? This is a revolutionary reframing of the question that caused people to step back and say, wait a minute, why are we using the energy? For doing what? What is the end use that is desired? Because people don't need to buy energy, of course. They use energy to reach some purpose. Keep yourself warm, go from point A to point B, or whatever, keep your food cold. So we'll go deeper into these examples, but you would begin to see how this reframing of the question changed everything in terms of how the societal leaders, policy leaders, and technical leaders think about energy problem. We'll go into technical details in a minute, but this is a good time to step back and also point out that art paid a great amount of attention to the future generation, right from that time onwards. He was a vice chairman for a new interdisciplinary group founded on UC Berkeley campus called Energy and Resources Group, ERG. And Energy and Resources Group was founded to train only graduate students. Only now, like 2 years ago, they started an undergraduate program. But until then, from 1970s until a couple of years ago, it was only open to people who already have a bachelor's degree in some field. Doesn't have to be engineering, doesn't have to be even science. Could be philosophy, could be mathematics, could be something else. And the goal of Energy and Resources Group was to create the next generation of leadership for United States and for California who can solve difficult interdisciplinary questions at the interface of technology, science and policy, and the environment. These are difficult questions that cannot be solved by single discipline study, however deep. In fact, the deeper you dig into a single discipline, the more difficult it becomes to talk to other experts. So the purpose of ERG was to actually create people whose strength lies in looking at the connections that have to be made across different disciplines. And he was a vice chair for many, many years, and the first vice chair of Energy and Resources Group. He also founded the American Council for Energy Efficient Economy, ACEEE, as it is belongingly called, is a nonprofit that is focused on helping do the analysis to help legislators and policymakers make the right decisions regarding energy efficiency whenever their policies impact energy efficiency. And almost everything they do has some connection or the other. ACEEE does that analysis. So a couple of concrete examples. Under Art's leadership, scientists at Lawrence Berkeley Lab discovered that ordinary fluorescent lamps, which used to have a magnetic ballast, iron core and copper wire, could be fired up with electronic ballasts, which were running at 40 kilohertz. And that would be lighter, easier to produce, but more importantly, would produce 10% more light per lamp, which meant that in every building, you would use 10% less energy for lighting. And typically, a building uses about 30% of its energy for lighting. So now there's a 3% reduction, not something to be scoffed at. It turns out that what was used for tube lights was made very small and put into the base of the bulb. So that's the basis of how we could use now around the world compact fluorescent lamps that can be screwed into the same socket as an incandescent light bulb. So the foundational work comes out of electronic ballast for tube lights, which was done because they are more energy efficient, just compared to magnetic ballast. I should also point out, and you know this, that a compact fluorescent lamp itself will use 4 or 5 times less energy than an incandescent lamp anyways, just because of the physics of the lamp. Another development was a heat mirror window pane, where this is the window pane, a double pane window, usually filled with argon gas, so it is sealed, and it has a spectrally selective coating on one side so that short wavelength infrared radiation from sunlight on a hot summer day is reflected outside, but short wavelength visible energy from sunlight comes right in, so your window looks like normal because visible light comes right through, but short wavelength part of the solar spectrum is rejected outside, so it doesn't heat your house. These windows are now common. Most of the windows in the United States now, 80% of the windows sold in the United States now have spectrally selective coatings. My house has windows with spectrally selective coatings. We don't need air conditioning at all because the house remains cool, because all the solar heat gain, the infrared part of solar energy is rejected outside. And all you see is clear, transparent, white window glass because the light comes through, much like shown here. But at the same time, you have on the winter night side a way to keep the long wavelength infrared inside the house so that your heat losses are also reduced. So you are now doing something where you are protecting heat loss at night on the winter night, and you're rejecting heat gain on a hot summer day. These windows are truly revolutionary in terms of how much energy it has saved in buildings, and it's an application of physics to building science to do something that is practical. Art took personal interest in trying to understand how do you make new buildings more energy efficient. Buildings, as you know, have a long life. So my question was at that time, I was this graduate student, I was saying, Art, most of the buildings in America are already built. Why are we worrying about new buildings in America where the renewal rate of building infrastructure is only 1%? But that was 1975. By now, 40% of the buildings have been replaced. 1% per year, 40 years later, right? So you see how the vision is not always near-term quick gains, but a vision that says if we continue on this path, it will lead to long-term positive impact. The software that he personally took interest in led to building energy efficiency standards for the state of California. No new buildings can be built unless they meet a certain building performance standard, which is validated before the building is built through this software. DO2 is a program that is a de facto standard around the world for predictive use, predicting energy use in buildings before you build a building. Another example that Professor Lee referenced is the example of refrigerators and air conditioners and many other appliances. Here is what is happening in the real world market. All of us as consumers are sensitive to the first cost of an appliance. So as consumers, we would tend to buy a cheap refrigerator, identically looking to a more expensive but less energy consuming refrigerator, because we are sensitive to the sticker price at the store. If that is what happens, then all the refrigerator manufacturers try to sell you the cheapest first cost refrigerator, which is hugely energy consuming. And we all take them home, we all plug them in, and the societal carbon footprint goes through the roof. So Art's thinking about this was, let's figure out how to do it right. California has an energy commission, and he argued to the Energy Commission staff that they need to design and develop standard tests for energy performance of refrigerators and disallow those refrigerators which are energy guzzlers, even though they are highly, looks like they are cheap, and that's what they will crowd out the more efficient, slightly more expensive refrigerators. So the state of California announced what are called appliance energy efficiency standards. And this is what happened. I'm going to give you just one example of what happened to only domestic kitchen refrigerators in the United States as a result. Because once California announced the standards, California is 10% of the United States. The manufacturers found it not worthwhile to make two different production lines, one production line for California, another for the rest of the country, so they all switched to the California standards. So the whole country benefited as a result of leadership of the state of California. This graph shows you on this axis the energy consumption per refrigerator in kilowatt hours per year. And this is that energy consumption, climbing, 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 climbing up until it was about 1,850 kilowatt hours per year in the year 1975. This is the standard so-called 16 cubic feet refrigerator. When the refrigerator standards were announced, they were announced with a delay that they will go into effect 3 years from the date of announcement, so that manufacturers had time to readjust their factory production. They could put in more insulation, they could put in more efficient motors, larger evaporators, larger condensers, more efficient refrigerator, better gaskets, and better sealers, and so on. The energy consumption of domestic refrigerators of the standard kitchen model have dropped continuously. Every drop is associated with the energy efficiency declaration, 3 years delayed, all the way coming down. The latest one, this graph ends at 2007, but the latest one goes to about 4,500. It's somewhere here out at this point. And in every case, the standards were designed so that the consumer actually saves money in terms of net present value. It was simply trying to protect the consumer from a tendency of paying attention to the sticker shock. It's not like the consumer is actually paying more, because effectively the consumer earns more by saving on electricity bills over the life of the refrigerator. I also want to point out that the size of the refrigerator went up and up and up, okay, until it levels off because it doesn't fit into the kitchen door anymore, so you can't make it any bigger. So the largest refrigerators are, this is the refrigerator volume in American units of cubic feet. So that doesn't grow up very, very high, but the refrigerator consumption declines. And note that even though the refrigerators were getting more and more efficient with better insulation, better gaskets, better motors, better evaporators, better condensers, the refrigerator price in constant dollars kept on dropping steadily. And it has continued to drop steadily. So that's part of the industrial learning curve as well. So we have truly a win-win-win by opening the door to asking the right question. Art ended up avoiding having to install 150 gigawatts of nuclear and thermal power plant that would have been along the coast of California. One plant every 3 miles was the prediction of what California needed by Dr. Ronald Doctor of the Rand Institute in 1975. And it turns out that California's peak electricity demand has remained flat at 60 gigawatts all the way from 1975 until now. He worked in policy, was appointed the commissioner of the California Energy Commission in the year 2000 by Governor Gray Davis, and confirmed and continued under Governor Arnold Schwarzenegger, and is a good friend of Governor Brown, who comes to consult him from time to time. After all these complicated effects, here is a simple summary of what California has done. Here is the energy consumption, kilowatt hours per capita. California remains flat at about 7,000 kilowatt hours per person per year. And the rest of the United States climbs up and up to about 12,500 by the year we go to 2014. And this is the avoided energy use, which is what I refer to as avoiding building many power plants. How was this achieved? Three major ways to think about this, and every one of them had a significant or leadership contribution from Art Rosenfeld. Utility programs and market effects. This refers to the effort in California of decoupling, the so-called decoupling of utility income from utility profits. A decoupling means the following. Because energy utilities are a natural monopoly, energy utilities, because you can't have 2 or 3 utilities hanging wires to your house, right? So they're a natural monopoly. They're always publicly regulated. So electricity prices, for example, are publicly regulated by California Public Regulatory Commission, PUC, okay? Public Utilities Commission. So now Public Utility Commission says to a utility like PG&E, we will let you make a little more profit if you agree to spend a few $100 million promoting energy efficiency. All you care as a private investor-owned utility is profit for your stockholders. We'll let you make that little more profit by jacking up the rate a small amount. But then in exchange, you must spend a few $100 million in giving subsidies for compact fluorescent lamps in homes and hotels, in giving subsidies for insulation in the ceilings of building roofs and attics, in giving subsidies and promotion of more efficient air conditioners or more efficient refrigerators. So as a result of this decoupling, California utilities it's not only $100 million now, it is more than $1 billion now. They spend more than $1 billion every year giving advertising, education, and technological assistance to reduce energy use among their own customers. At the same time, they make little more profit because the PUC says, good, we will make sure that your programs are really cost effective. So we have very large monitoring and verification programs, M&V programs as they're called. And with those M&V programs, the utility says, this is in societal benefit. The customers gain money by having energy efficiency. The stock owners gain money by getting a slight bump in their return. And overall, our carbon emissions go down or remain constrained. So that's this part alone. The appliance standards we already discussed. And building standards we also discussed. The building standards, the Title 24 refers to the name of the law. The building standards are the standards that say that you cannot build a new building in California unless it meets a certain performance as predicted by a code, a software code that has been standardized and tested like DO2. So these standards are tightened every 3 or 5 years, so it's not a one-time thing. But whenever they are tightened, everybody has about 3 years to accommodate the new standard before they are met. So nobody gets an economic shock from a sudden rise in the expectation of the standard. At the same time, they know it's coming, so they prepare for it, they work for it, and this is the effect finally. I want to also show an example of catching small gains. What I mean by catching small gains are simple things where you think it is so simple, it is like, what? Why is art paying attention to it? So here is an example about having dark colored rooftops. Most buildings have dark colored rooftops because in California, maybe around the world, people like or traditionally have put on dark colored roofs, whether they are shingles, which are dark colored, or maybe roof tiles, or maybe dark brown roof tiles, and so on. Now you can ask the question, what happens if the roof was painted white? You have to paint the roof anyway. The shingles have to be replaced anyway on a cycle of maybe 6 years or 5 years or 10 years, depending on what happens. So as you replace your roof, if instead of replacing it at the same color, which is typically albedo of 0.2, albedo is a fraction of sunlight that is reflected back into the sky. If the albedo is 0.2, suppose you replaced it with the roof whose albedo was 0.8. So it was almost light gray or almost very light gray, okay? I'm not saying 0.9, 0.95, though you can have a roof of that high albedo. If you do it that way, effectively, you are rejecting a lot of sunlight that hits the roof back into outer space, okay? So shorthand, you are essentially saying there is less heat contained on the planet Earth now because your sunlight is not being absorbed on the planet Earth. Visible short-wave sunlight is being reflected from the rooftop back to the outer space. And you can say if I change this albedo from 0.2 to 0.8, and therefore I contain less heat, I capture less heat on the planet, what is the equivalent amount of CO2 reduction that this has achieved? Now that takes real careful engineering science. Art actually drove that science carefully to the point that it is now accepted worldwide that changing the albedo of a 10 square meter roof, a 1,000 square foot roof, from 0.2 to 0.8 is equivalent to one-time reduction of 4.2 tons of CO2. Because now you have that much less heat being captured. So many, many places are now requiring, including California, is requiring that when buildings change their roofs, commercial buildings change their roofs, they must change it to a light-colored roof. So this photograph shows San Jose, California in 1993, before Title 24 went into effect related to rooftops. And this is a photograph of the same site after 2011, 5 years of Title 24. We can see the same, it's no incremental cost. You're going to paint the roof anyway. The only point is when you replace the roof or repaint the roof, it just goes to a light colored shade. Many cities are putting in the ordinance. For example, New Delhi, the city of New Delhi has a law that says all government buildings, when they repaint or rechange their roof, it must be light colored roof. Because you're essentially getting almost 4 tons of CO2 savings per 10 square meters for nothing. So in short summary, he's a distinguished scientist emeritus at LBL, doctoral advisors to a bunch of us, founder of ACEEE, founder of Energy and Resources Group, and also what is called California Institute for Energy and the Environment, senior advisor to the Department of Energy, and a long distinguished career for California Energy Commission as a commissioner. Selected prizes and awards is a long list: Leo Szilard Award, Sadi Carnot Award, Berkeley Citation, Enrico Fermi Award, the Global Energy Prize, and the National Medal of Technology and Innovation from President Obama. And I'm very, very happy to say, and he's very happy to receive the Tang Prize for Sustainable Development. He's most proud among the prizes he has received about the past, about the Enrico Fermi Award, because Enrico Fermi was his own thesis advisor. So it was a very big deal for him to receive that award 10 years ago. That was on his 80th birthday. And now, on his 90th birthday, or birth year, I should say, it's a great distinguished honor for him and great pleasure for all of us that he's selected to be the recipient of the Tang Prize for Sustainable Development. Here is a picture of Art receiving the National Medal for Innovation, NMTI, Technology and Innovation. A quote from Professor John Holdren, who teaches normally at Harvard, but is now the director of the Office of Science and Technology Policy for the White House, saying art had an enormous impact on US energy policy starting in the 1970s with insights, quantitative analysis, pointing out to the potential for increased end-use efficiency as the cheapest, cleanest, and surest response to the nation's energy challenges. Art, this is a photograph taken 10 years ago when he got the Fermi Medal. He demonstrates how to take interdisciplinary analysis and actions to solve complex challenges of sustainable development facing this century of human society. He's an inspiration truly to thousands of people. This is his picture when he came to Berkeley as a young professor. And I want to end with a quote from Art Rosenfeld about the future of what we have to do. Art says there is no law of physics and no law of nature that prevents human society from achieving long-term prosperity and sustainable development. However, our success or failure to do so rests entirely in the choices we make and the actions we will take. And with that, I thank you very much.
Well, Ashok, thank you very much for really wonderful lecture, very delightful, enlightening. Since we do have a few minutes, Dr. Gaggio will be happy to answer some of the questions. Not many. Short questions and short answers. Are there any questions?
This one.
Well, Professor Wang Baoguang, please.
California has the lower energy consumption to the average of America. What's the difference? Why? What's the reason? This is my question. Thank you.
So let me repeat the question. Correct me if I misunderstood. The question is, what is the reason why California has lower energy consumption than the rest of the United States? And there are different analyses done by economists. Part of the reduction in California energy consumption is attributable to, let's go back to that slide. Part of the difference here is already because California has a milder climate, you could say. But we were using in our homes the same amount of energy for heating in California that we were using in Minnesota, right? So I think we were not very smart at that time in energy efficiency. But we have a milder climate, so that helps for sure. Secondly, going forward, California has implemented policies that have actually changed. This is actually a projection of how much conservation savings took place from 1980 to 2006. And these savings are 45,000 gigawatt hours of savings, cumulative savings. This is the area under the curve. Okay, this is the area of this triangle. From 1980 to 2006, and this is the height, so the area is given by the total amount of savings. And these are the causes of why these savings occurred, right? The third cause is that some of the heavy engineering production industry in California moved out of the US altogether. Over the last years from 1980 to 2010, last 30 years, heavy engineering production moved out of even United States, not just California. So there is some contribution from there as well. So I cannot take the viewpoint that everything is because of energy efficiency. But a major contribution definitely is from energy efficiency. There was a question here.
Thank you for giving such a wonderful talk. For those people who been to United States, envy so many people can live in single house. I suppose you own one too. But it seems to me you're talking about building and housing style really influence directly or indirectly influence energy consumption. For example, public transportation, high-speed rail, like for between San Francisco and LA, seems very difficult to do. So we have limitation for land here, but I'm sure some of the country in the world, they really have land to build the style like LA. Can you have some advice and comment on how we should do the housing? Thank you.
So question is about advice on how to do housing, and you're quite right that individual family separate homes are less energy efficient inherently than apartment buildings. Because apartment buildings, essentially you're saving the heat loss or heat gain from the periphery. At the same time, apartment buildings, unless they are owned by the occupants, they have a disincentive in putting insulation in the walls or improving their windows, because apartment buildings are owned by a different landlord who doesn't pay the energy bill. So there are positives and negatives, but there are ways to address those barriers, like California did with the energy building code, by saying these buildings have to require certain level of energy efficiency no matter who owns it. So those kind of barriers can be removed through making appropriate building codes, much like we have a fire code, we have safety code, we have structural safety code. In California, we have earthquake code. Similarly, we have an energy code. So that way, everybody has to fall in the same line. So there are ways to do that, where you solve the problems of split incentives, as the economists call it.
Well, because time is up, we cannot ask any more questions. But I do want to say one thing. In the 70s, I was in the United States when the compact fluorescent lamp was invented. It was expensive. It said $20 a piece. Certainly nobody will buy it. Housewife will go to the market, might be in the pocket, she has $30, want to buy grocery, vegetable, meat, would not buy the fluorescent lamp. But when the policy was made, utility subsidized the fluorescent lamp. You can go to market, $1, you can buy 4 pieces. In grocery store, it's a pile of fluorescent lamp, and you can see immediately, within the couple of months, everybody used fluorescent lamp, and electricity consumption went all the way down. And that is the combination of invention of technology and policy matters. And what Earth has done is really very important, coupling the technology into policy and reduce the energy consumption. In Taiwan, we have a long way to go. Today, we have learned a lot, but we do have to work really hard to achieve sustainable development in the future. Well, thank you very much, Art, for such a wonderful lecture.
Pleasure.
Thank you very much to Dr. Lee and Dr. Ashok Gagil. Ladies and gentlemen, please give them another big round of applause to thank them. Thank you very much. Ladies and gentlemen, this is the end of the Sustainable Development Lecture Session. Thank you very much for your participation. 各位来宾，第2届唐奖得奖人演讲永续发展场到此圆满结束。非常感谢您今天的参与，祝您有个美好的一天，谢谢。